Welcome back to the Data Center Fundamentals series. In part 1, we covered routing fundamentals, static routes, administrative distance, metrics, and the basic logic behind route selection. In part 2, we moved into dynamic routing with OSPF and EIGRP. Now in part 3, we are going on one step further. We are going to look at BGP, how it is used in modern data centers, how underlay and overlay networks work together, how the control plane and data plane have different jobs, and how Nexus switches actually forward traffic in hardware. We will also look at VRF, verification commands, and a simple troubleshooting method. The goal is to connect all the routing concepts we have learned so far into one complete data center picture. Let's start with BGP. BGP stands for Border Gateway Protocol. Most people first hear about BGP when learning how the internet works, because BGP is the main routing protocol used between large networks and autonomous systems. But BGP is also very important inside modern data centers. Why? Because modern data centers need to scale. They may have hundreds or thousands of switches, many different tenant, cloud connections, external service providers, and multiple data center locations. BGP handles this kind of environment very well. One of its biggest advantages is policy control. With BGP, we are not only asking, can I reach this network? We can also decide which path we prefer, which routes we want to advertise, and which routes we want to block. So BGP gives us more control over how traffic moves through a large network. That is why BGP has become so important in modern data center design. Now let's talk about two words you hear very often in data center networking: underlay and overlay. The underlay is the physical IP network. Think about the actual routed links between leaf switches and spine switches. Its main job is simple: provide reliable IP connectivity between devices. The underlay does not need to know everything about applications or tenants. It just needs to make sure that one network device can reach another. Now, on top of that underlay, we can build an overlay. The overlay provides logical services. For example, tenant networks, VRFs, VXLAN segments, or EVPN routes. So you can think of it this way: the underlay moves packets between devices. The overlay carries the logical services on top of that connectivity. In many modern designs, BGP can participate in both. For example, eBGP may be used in the underlay between leaf and spine switches, and MPBGP EVPN may be used in the overlay to exchange VXLAN and tenant information. This separation makes the network easier to scale and more flexible. Before going deeper, we need a few basic BGP concepts. First, BGP works with something called an autonomous system, or AS. An AS is basically a network or group of networks managed under one administrative control. Each AS has an AS number. For example, one organization may use AS 65001 and another may use AS 65002. BGP devices create neighbor relationships called peering sessions. When two BGP routers become neighbors, they can exchange routing information. There are two main types of BGP sessions. eBGP is normally used between different autonomous systems. iBGP is used inside the same autonomous system. Another important point is that BGP uses TCP port 179. So, unlike protocols that directly build their own transport mechanism, BGP uses TCP for reliable communication between neighbors. BGP also advertises networks as prefixes. For example, 10.10.10.0/24, and instead of making decision based only on something simple like hop count, BGP uses different path attributes. Those attributes give us a lot of control over route selection. So, how does BGP choose the best path? This is where BGP becomes different from protocols like OSPF. OSPF mostly looks at cost. BGP looks at multiple attributes. Imagine the same destination is reachable through 3 different BGP neighbors. BGP examines the available paths and compares them step by step. One important attribute is local underlying pref. A higher local preference is normally preferred. Then BGP may look at the AS-path. In general, a shorter AS path is preferred. Other distributes can also influence the decision, such as origin, MED, whether the path was learned through eBGP or iBGP, and the IGP cost to reach the BGP next hop. If there is still a tie, BGP continues using additional tiebreakers. The important things to understand is this: BGP is not simply looking for the mathematically shortest path. It is choosing the path based on a policy-driven decision process. This is what makes BGP very powerful. Now we move to a very important concept in networking: the control plane and the data plane. The control plane is the part of the device that makes decisions. This is where routing protocols such as BGP, OSPF, and EIGRP run. The control plane learns routes, exchanges information with neighbors, calculates best paths, and builds the routing table. So you can think of the control plane as the brain of the switch. The data plane has a different job. It forwards the actual packets. Once the control plane has decided the best route, that information is installed into forwarding tables. Then the data plane uses that information to move traffic. So the control plane says this is the best path, and the data plane says, okay, now I will forward the packets through that path. The control planes think, the data plane forwards. Both are essential, but they do completely different jobs. Cisco Nexus switches are designed for very high-speed data center traffic. They cannot send every packet to the CPU and ask the CPU what to do. That would be far too slow. Instead, forwarding is performed in hardware. Specialized chips, usually ASICs, perform the forwarding lookups. The control plane installs route information into hardware forwarding tables. Then, when a packet arrives, the hardware performs a lookup. It checks the destination. It finds the correct forwarding entry. It selects the outgoing interface. It may also update layer 2 or layer 3 information, decrement the TTL, apply QoS markings, and then transmit the packet. All of this can happen extremely quickly. This is why Nexus switches can forward traffic at line rate. The CPU is still very important for protocols, management, and control plane operations, but normal packet forwarding happens in specialized hardware. That separation gives us both intelligence and performance. Now let's talk about VRF. VRF stands for Virtual Routing and Forwarding. A VRF allows one physical switch to maintain multiple separate routing tables. For example, imagine one Nexus switch supports 3 customers. Tenant A uses VRF blue, tenant B uses VRF green, tenant C uses VRF purple. Each VRF has its own routing table. Routes inside VRF blue are separate from routes inside VRF green, and routes inside VRF green are separate from VRF purple. This gives us a strong logical isolation while still using the same physical hardware. That is why VRF is so useful for multi-tenancy. It can also be used for business unit separation, management networks, shared devices, or security zones. Traffic does not automatically move between VRFs. If communication between VRFs is required, it has to be designed intentionally using route leaking or another controlled method. So the easiest way to think about VRF is one physical switch, multiple independent logical routes. Now let's look at some common routing problems. One obvious symptom is that a decision cannot be reached. Maybe the route is missing, maybe the next hop is unreachable, maybe a routing protocol neighbor is down. Another common problem is route flapping. This means a route keeps appearing and disappearing. That can happen because of an unstable interface, a physical problem, or a neighbor session that keeps resetting. Sometimes traffic is reaching the destination, but it is taking the wrong path. That may happen because of the wrong metric, BGP attribute, administrative distance, or routing policy. Policies can also block routes completely. Prefix lists, route maps, filter, or VRF configuration may prevent a route from being installed or advertised. The important point is that routing problems are usually not random. There is normally a logical reason. The job of troubleshooting is to find exactly where that logic breaks. When troubleshooting, verification commands are extremely important. Start with the interfaces. Use Show IP Interface Brief. This gives you a quick view of interface status and addressing. Then check the routing table, Show IP Route. This tells you whether the destination route is actually installed. For OSPF, use Show IP OSPF Neighbor. For EIGRP, Show IP EIGRP Neighbors. For BGP, Show IP BGP Summary. This is one of the most useful BGP commands because it quickly shows the state of your BGP neighbors. For more detail, Show IP BGP Neighbor. You can also inspect the routing configuration with Show Running Config and Section Router. And depending on the platform and feature set, hardware or forwarding table commands can help confirm whether routes have been programmed correctly. The key is not to run commands randomly. Use each command to answer a specific question. A structured process makes troubleshooting much easier. Step 1. Identify the problem. What exactly is not working? Is one host affected, one subnet, one application, or the entire network? Step 2. Check the basics. Make sure the interface is up. Check the IP address and subnet mask. Check physical connectivity. Make sure the interface is not administratively shut down. Step 3. Verify the route. Is the destination route is the routing table? Is the next hop reachable? Are the routing neighbors up? Step 4. Analyze the details. Now look deeper. Check metrics, administrative distance, BGP attributes, policies, logs, and protocol state. Step 5. Fix the issue. Make one control change based on the cause you identify. And finally, validate and monitor. Do not stop just because one ping works. Confirm that the routing table is correct, traffic follows the expected path, and the problem does not return. A calm, step-by-step process is usually faster than jumping randomly between commands. So, which routing method should you use? Static routing, OSPF, EIGRP, BGP, VRF? There is no single answer. Static routing is useful when the environment is small and predictable. It is simple and easy to understand. OSPF is a strong choice for internal routing, especially in multi-vendor environments. EIGRP can be useful inside Cisco-focused environments. BGP is excellent when you need large-scale routing, strong policy control, cloud connectivity, service provider connections, or modern data center fabrics. VRF solves a different problem. VRF is about creating separate routing domains and isolating traffic. So in real networks, these technologies are often used together. For example, BGP for routing, VRF for tenant separation, and hardware forwarding for performance. The right choice depends on the size of the network, the topology, scalability requirements, vendor environment, operational skills, and business needs. Let's summarize part 3. We started with BGP and saw why it is so important in modern data centers. BGP provides scalability and strong policy control. We looked at underlay and overlay networks. The underlay provides IP transport. The overlay provides logical services and tenant connectivity. We covered basic BGP concepts like autonomous systems, eBGP, iBGP, prefixes, and path attributes. We also looked at BGP path selection and how BGP uses policy-driven attributes to choose the best route. Then we separated the control plane from the data plane. The control plane learned and decides. The data plane forwards. We saw that Nexus switches use hardware forwarding to move packets at very high speed. We also covered VRFs and how one physical Nexus switch can maintain multiple isolated routing tables. Finally, we looked at verification commands and a structured troubleshooting process. So routing on Nexus is not only about learning commands. It is about understanding how the control plane, forwarding hardware, routing protocols, policies, and logical separation all work together. And that completes Season 1, Episode 8, Nexus Routing Basics. Across all 3 parts, we moved from basic routing concepts to static routing, dynamic routing, OSPF, ERGIP, BGP, VRF, and Nexus hardware forwarding. In the next episode, we move from logical connectivity to physical connectivity. Season 1 Episode 9 Data Center Cabling. We will talk about copper and fiber cabling, transceivers, connectors, patch panels, cable management, labeling, and data center cabling best practices. Because even the best network design cannot work without reliable physical connections. If you enjoyed this series, subscribe to Next Layer Tech and follow the Data Center Fundamentals series. Thanks for watching, and I'll see you in the next episode.